topic is resizing images. So the main problem now would be to reevaluate the images at locations that we look at. Let's do some split here. So let's say that we have an image that is continuous. So this image whatever there, and then you have it defined for everything that we have, that has this. So it is the continuous image. And this continuous image, we are discretizing some discrete screens with a pixel size we will call TS for sampling rate. And then we have the version that is this. This one is this one is continuous. But let's say that you are given the discrete one. So we have somehow represented also that thing. Let's use the colors. So let's say that. We are given the discrete one. So like this. So we are given the discrete. So somehow this is the discrete version. And we want to reinterpolate it at a finer or a thicker pixel size. So let's say I want it to be smaller. So now the pixel size is bigger. So in my example it is bigger, but it could be also smaller. So how do we go from the discrete samples here? How do you go to the discrete samples in this one? Okay, so that is called a reinterpolation problem. Reinterpolation. Or an interpolation problem, or resampling, or however you want to call it. This is the problem that we will solve today. And we will introduce 3 interpolation schemas. So we will use nearest neighbor. We will use bilinear interpolation. And then we will use bicubic interpolation. So let's see. Okay, so then let's start with nearest neighbor. So you see that this is the original image that is already in discrete. And then you want to interpolate. And you see that depending on what is your interpolation scheme, you will have more or less details. So the nearest neighbor is the one with less details, and the other two, as you go down, you have more and more details. So let's see how to do that. So let's say that we want to enlarge an image. So we want to make the pixel size smaller. So let's say that we want to go from this image to this one, where the pixel size is here is smaller. So we have more pixels to cover the same area. So you start with an empty kind of image where we will copy the pixels that are coming from this one. So let's say that we want to make an enlargement by factor 4. So I will take every pixel here. So we take 1 pixel, then 3 zeros, and then another pixel, 3 zeros, another pixel, 3 zeros. And these are signals. You have seen that operation. It was called upsampling. So let us see the signals. So with signals, we have an input signal. Then you go through the upsampling by a factor of 3. And you have the upsample signal. this, just 3 samples so that we can easily recognize which one is bigger. And then when we do the upsampling, it will look like this. So let's say that our upsampling is by factor 3. So it will look like this. Say, this one, this one. This is XD, right? This is 3. Have you seen this operation? Yeah. Okay, so here you have this is equal to x n divided by d if n is a multiple of d and then 0 otherwise. So this is our upsampling operator. So we will do upsampling, but now in 2 dimensions. So you see the d here in my example, d is equal to 3. So this is 0, 1, 2, 3, and that xd of 3 is equal to x of 1. So now here in our image, d is equal to 4. Then we are doing that sampling in both directions. So you have a sample of 3 zeros and then another sample of 3 zeros and so on. So you start with empty and then you fill it this way. And this is the upsampling to that. So this is just to show how it looks like. And then, so we have already filled the values here in the corners. Okay, so you can imagine a corner here, a square. You see these squares, and we have filled only the values in the corners where the red dots are. So, and now how to fill the rest of the square? So you simply copy this one. So that would be a possibility. So you have the values at the corners, and then you simply copy. That copy, you want to do it in one dimension. So one dimension, what you can do is a filter H of n, and then the age that you need for that. This age also depends on the age that you need for that is this one. HD, then when d is equal to 3, is this one. So you are composing this output that has one sample and 2 zeros. You are composing with this one, and then you are filling 2 gaps. And it's just a convolution with this. So what we are doing is first we upsample and then we compose. Yeah.
I don't understand why
HD is the one that will perform this step of filling the gaps. So you have sample then zeros, then another sample then zeros. So these gaps, you want to copy simply the one on the left. And that you can achieve by convolving with a curve.
the red dots are the ones that
Yeah, these ones. So these we have, and then we have marked with the red one. Yeah. Okay, so here in 2 dimensions it is the same, but now the kernel looks like instead of as a step in 1 dimension, it looks as a step in 2 dimensions. Okay, so yeah, this is a simply enlarging. And then we can have the opposite. So we may go from a large image to a small one and do that in 1 dimension. So that are the equivalent. So we have in 1 dimension, we have x of n, that goes into the downsampling. Let's make it the same. So let's say that this is going to be then we have x, d, and this x domain will be x of d n. Yeah, actually that's not right. It will simply be x of d n, x of d n. So if you have something like this, or let's say you have x of n, this is n, then x d of n we have x d of n. Let's put numbers. So let's say that this is 5, 4, 3, 1, 4, 3, 1, and zeros. We will have 5. Let's say that b is equal to 3 again. Then this is 0, 1, 2, 3, 4. Then we will have 2, and then we will have 0. Okay, so that is all we have to do here. So we will take 1 every d pixels. So these are the pixels that we will take. So this is a zoom of this image. And then we will take only the red pixels. So these are the red pixels. And then we construct the new image by simply copying the ones that are clean. Okay, so very simple too. So this scheme, this scheme is called nearest neighbor resampling. Nearest neighbor because we have taken here it is really clear. Here it is very clear. So we look for filling these pixels. We take the nearest neighbor to the left. So take the nearest neighbor left and top. Okay, so then what happens if we want to have a fractional factor? So yeah, something important. Let's go back to here. So let's say that let's use the same colors as I used before. So let's say that this pixel size is px. So it's a pixel size here. It's px. And same above. So let's say that pixel size px. So the pixel size at this point is ts divided by 2. Okay, so we see that there is a factor. So this ts, the ts prime, ts at the output is always a factor multiplied by the original one. So let's make the original one. So let's so it is always some factor times the original. So what if my factor is not an integer, but it is a fraction? So let's say that I want to do a fraction, so an enlargement by 3/7. So what I can do is, okay, I want to reduce by 3/7. So I will divide the original image in blocks of 7 pixels because of this 7 in the denominator. And then I will take the 3 pixels in each one of the squares. So I will take this one, this one, this one, so the ones that are highlighted. And then you simply copy. That would be a possibility. But you see that there is a problem, that this sampling is not uniform. So distance between these two pixels is 1 in the middle, but the distance between these two is 2 in the middle. So now our sampling is not uniform. That is what we will try to solve with the linear. So then we can simplify those ones. These are pixels that we are copying. Then we will put them together into an image, and that is our example image. So this will be the downsample image with this scheme. Okay, so then, yeah, so we have the original, the reduced one, and then a zoom version of it. And you see these kind of high frequency pattern, this is aliasing. So we haven't seen aliasing in this course. But when you know that when you sample at a given pixel size, you may have aliasing. Yeah, this is. Okay, so now let's do the opposite. So we have a small image, let's make it big. So okay, we will construct blocks. I think that is some nice image. So we will construct blocks of size 7 times 7, and then within these big blocks, we will copy the 3 pixels. So we divide this one into 3 times 3, the output into 7 times 7, and we distribute these 3 times 3 pixels in the 7 times 7. So this is the distribution, and you see again that we have an uneven distribution. And then this nearest neighbor resampling. So you look for the nearest neighbor top left. Okay, so for filling this one, we use this information here. For filling this one, we take this information. And so you look for the nearest neighbor that we have, like top and left. So this is what we take resampling. Yeah.
Lo español. Porque cuando la hacemos pequeña, hacemos 3 entre 7 y cuando la hacemos grande, 7.
Because the pixel size is, must be bigger or smaller, so when you go in this direction, so you have you are starting with a big image and you want to make it smaller, so you have to divide this one into blocks of, so 7 pixels here will be 3 pixels here. Your final image will be smaller. Okay? So when you're making it big, it's the opposite. That will be the opposite. 3 pixels here will be 7 in the next one. And 3 and 7 is just an example. You understand that. Okay, so now, yeah, I think this is way too complicated. I think that important message is this one. So there is a scaling factor. I will do it in the whiteboard. But the output at a given point will be the input at some location. And this location is given by rounding some fractional coordinates. And the fractional coordinates are this one. Okay, so let's see these difference. So let's use the same color. So let's say that this is our input. This is our output. These are R and C line sizes. This one has R and C. And then here you have coordinates 0, 0. have coordinate 0, 1, and coordinate 0, 2. And the same here. Okay. Here you go to C minus 1, here you go to C prime minus 1. So now I want to find the output. This is my output. I want to find the output at the location R prime C prime. R prime C prime. So let's see how to find it. So I know it will be the input at some point, but I don't know the point. Which point should I take? I will call it R fraction and C fraction. And let's compute those. So let's think which is the length of this side. The length in the original analog image, so in the continuous image, this length is CTS. And here it will be CTS prime. So this will be CTS prime. And those two lengths have to be the same. So this length, so I have an image here. This length and this length have to be the same. So we know that I will change colors. So you know that CPS is equal to C prime PS prime. So what is the ratio between any coordinate here? So the one that occupies position C, here it occupies position C prime. Do you agree with that? So there is a scaling. So this C has to go to C prime. So there is a scaling. That is the C prime location is C divided by this. So this point has to be coming from that. So there is a scaling factor, that is this one. That is the change. Okay. So if I want to go from this point to that point, what I have to do is copy the scaling factor. The scaling factor is C divided by C prime. C divided by C prime. So you have to take R prime. So I take R prime C prime, and then I multiply by C divided by C prime, R prime. This goes with that. R divided by R prime, and C divided by C prime, C prime. So this is the location I want to look for. If let's go for C. So if my column is C prime, this is capital. This is capital. This one is small. So if my column is C prime, I divide by C prime and multiply by C. So if I'm there in the corner, then this ratio is 1, and then 1 times C is equal to 0. You see? So there is a scaling factor that are these two ones. So these two scaling factors. This is the scaling in rows, this is the scaling in columns. And that is the point that we want. But it may happen that this is 3/7, 3/7, something like that. So in general, these coordinates are not not integer coordinates. That is why we have called them fractional. So if you want to, you cannot copy from a fractional coordinate because you don't have it. It is like I have so let me draw one of these pixels. So let's say that we have very big pixels. And these are the points where I know the value. But then these fractional ones, this fractional, tell me you have to interpolate there, but they don't have the value there. I have to have it here in the middle of the pixel. So that is why I look for the nearest neighbor, the nearest is this one, and then I copy. So what I have to do is copy from I, and then you round the spectrum at F, CF. And you have it. So this rounding is this little vector that moves you to the location where you have the values. Here you understand now the name is name. So it's nearest neighbor. We are in this domain. Yeah, the green point. Okay, so this is what this slide is explaining. Then, so there are a lot of slides related to this, but that we have explained. So you don't have to follow exactly the slides in the same reasoning that is. So what is important here is this thing. So you have a coordinate in the output. That coordinate you have to scale it to the original space, and the scaling is are these ratios here. And then that coordinate will be fractional, and then we have to look how do I get this value when I know nearby values, but I don't know exactly this one. And then the solution of nearest neighbor is take the value, and then you have the coordinate. Okay, so then we can do it in some other way that will be called bilinear interpolation. So bilinear interpolation, this is nearest neighbor again. Nearest neighbor is for pixel replication, so you have a value that you replicate. So what if we can, so we know the images are the red points. So what if we interpolate the values in between so that we make a smooth transition that this square here. So this square here has a smooth transition from black to white, from black to white. So the transition is smooth, while in the previous one, it's a very hard transition. So you go completely black, 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 and then at some point you have a big jump to white. So by not making a smooth transition. So that is what we will do. So in general, this happens here the same. So we have these big pixels. I know the value at these four corners. So why not to use the information from the corners? So I look at the 4 pixels around, and then I interpolate the value here using the values that I know. I know these 4 values. The 4 values at the same time. So that is what we will do. So let's say that these are our 4 corners. We know the values. And I'm asked to evaluate somewhere else. So let's say that we want to evaluate there. So why not to use the 4 cells around? And then what we will do is to build the surface. So we will construct the surface here, such that the interpolations are done with lines. So let's see. So we construct the surface, and this surface will go through the 4 corners. So we have some surface, and then we look at this side. So we look at this side, and this pixel that we got is in the middle. So we will evaluate this side, and this side is a line. Okay, so we will evaluate this side at this location, and the same on the other side, and the same on the other axis. So we have it on the other axis. So we have this side, this side, this and this, and we will evaluate at these 4 corners. And then we evaluate this point as the intersection of this. And this is a line, this is another line, and that is why it's called bilinear. That is a nice picture on the web. I think it is in the Wikipedia, they have a nice picture. Yeah, this is the one I'm looking for. So we are filling a surface, and in this surface, we will join these 2 points with lines. So these lines, these are lines, and they are not curves. This is in this way of curves. So this is a line, this is another line, and we will interpolate at this point and this point, and then merge or join with another line and evaluate that line at that location. So we are fitting lines and then evaluating those lines at a given. So this looks like a plane, but it is not a plane. This is a surface. Okay, good. Okay, so now this would be the result. So I have explained how to interpolate this one in the middle, but I can also interpolate the one on the edge. So the one on the edge is just evaluating here the line. So you can now fill everyone. So now let's make the zoom. So let's make an image bigger by a factor of 4. And this would be its neighbor. Okay, so these are the points what we know. And then so this is the result of its neighbor. And this is the result of bilinear interpolation. Can compare the 2. See, so it is completely different. One is very smooth, the other one is somehow having jumps. More comparisons of the same. And now here is another comparison where we have to interpolate. So the yellow squares are where nearest neighbor interpolation is taking the sample from, while this would be the fractional coordinates we would like to. Bilinear interpolation is able to get the value from the red squares, while nearest neighbor cannot take from the red, it approximates by the nearest neighbor, and that is why it's taken from the yellow ones. But now the distance between any 2 red squares is the same all the time. logs of 7 times 7, but now the distance between red points is uniform in all directions. Okay, so then let's have a look at one particular one. So let's say that we have to interpolate there, so we have to interpolate at this point that we have the 4 corners. So how do we get those values? I'm just saying there, so examples. Okay, so let me, I think, yeah, this one is good. Okay, so we have the 4 corners, and we have the 4 corners, and you want the value here, that is row fractional, column fractional. And then you can measure, so the nearest neighbor, if you round to the floor, so let's say that this is 2.3, 5.7. So 2.3 rounding to the floor will be 2, 5.7 rounding to the floor will be 5. So this is the point 2.5. And if this is 2.5, this is 2.6, this is 3.5, and this is 3.6. So in general, if this is RC, this will be RC plus 1, this will be R plus 1C, and this is R plus 1C plus 1. So now we can measure what is the distance from our point to each one of the corners. So let's call this distance, let's call it delta C. This distance, let's call it delta R. If this is delta C, this is 1 minus delta C, and this is 1 minus delta R. So now we can give more or less importance to each one of the 4 pixels, depending on how close you are to them. So we can measure these areas. Okay, so we can measure this area, this area, this area, this area. So let's say that we are very close. We are very close to this corner. So very, very, very close. So let's say that delta C is almost 1. Okay, both of them. So I think it would be more important. So we should give more weight to this one than to any other pixel. So in the limit, if we are exactly at that pixel, that would be the only one that should contribute. Okay, so let's say that this is 0.99, 0.99. So you are really, really close to there. So this one, we get a high weight. This is almost 1 times 1. So this is getting weight 1. This is getting weight 0. Because delta R is 1. So this is 0. This is 0 and this is 0. So the only pixel that contributes when you are in this corner is this one. Now let's say that you are in the opposite side, so you are here. So now delta R and delta C are 0. So this weight is 1. So we will multiply this by this weight, this by this weight. So these are the weights, these are the 4 pixel values. So this will get weight 1. This will get weight 0 because delta R is 0. Delta C is 0. Here, both of them are 0. So the only one contributing is this one. And for any one, it doesn't matter in which corner you are, you can analyze this carefully and you can see that only the right pixel is contributing. If you are more or less in the middle, then the contribution of each one depends on the area that it has between your pixel, your fractional pixel, and the 4 nearby pixels. That is what in this drawings you will have. So this representation is here. It's also showing that. So if we have these 4 pixels and we want to interpolate there, so what we should do is this one times this area. Then this one times this area. the green times this area, and the red one times this area. That is the area that is the opposite direction. See? Okay, so this is the main idea here. So the fractional, so the scaling factors are the same. So it's exactly the same scheme that we had before. But now, instead of using rounding, so let's make, I don't know, using interpolation to be this one. So instead of rounding, what we are doing is evaluating I'm not using equal, I would say approximately equal, so that I can continue. So this will be the bilinear operator is the 1.5% RFCF. So the location is the same. So the location only depends on the scaling factor. But how you get the value from the original image for nearest neighbor is just rounding and copying the value. This bilinear, it is a multiplication with the areas to get the value from the four nearby pixels. So the next idea is, okay, so all these are details we don't care. This is an illustration of that idea. So how you manage it, you have color images. So instead of using points, so scalar values. So this is a vector, and this is a vector. Simply multiply the vectors by the weights. So these formulas, you see, they have been defined with vectors. So it is the color vector at that point. Okay, then why to restrict to just 4 points? Why not? We will not see the mathematical detail of this one, but the idea is this one. So why to restrict to just the 4 nearby points? I can take 16 nearby points. Then I can fit another surface. And these are polynomials of degree 1. You have 4 points. Now you can evaluate, make polynomial of degree 3. This going to this direction, this one, this one, this one, and then for the columns. And then you evaluate these polynomials at the notations given by the fraction, and then you can join by then you evaluate the multiplication value. So instead of here we are feeding polynomials of degree 0. Here we are feeding polynomials of degree 1. Here polynomials of degree 3. And that is the name B cubic because it is cubic. Polynomials of degree 3. And B because you are going in the 2 dimensions. So we will not see these details. Yeah, you see that there are some polynomials of degree 3 that are involved. And the scheme is the same. So you have to take the nearby pixels. So you have to look for all of them. And each one of them will be multiplied by a weight. And this weight is given by a polynomial. And then you can see some results. So this is the original image, and this is the image interpolated with nearest neighbor, with linear interpolation, and with cubic interpolation. So we are making it smaller because we are making it smaller. The sampling rate is bigger, and then we can have aliasing. So you see the aliasing here. So here in the windows that are high frequency components, you see the aliasing. And in the bilinear, you see it a little bit. In the bicubic, you don't. nearest neighbor, bilinear, cubic, delta bilinear, then yeah, the cubic is the most accurate in making these interpolations. So estimating what is the value at the given point. But this is also the one that makes more calculations. So I was interested in the flag, to see how it was done with the cubic. So the artifacts you always see in the high frequency components. The low frequency components you don't care. If a region is very flat, you don't care because it is all the values are the same. So when you take all these values, so if the image is very flat, all these values will be almost the same. Then these curves will be very close to just a line, or just very close to just a constant. So you care about these things when you have oscillations, and the curves can show much more accurately. Okay, any question on this part? So that was the lecture that we had today. And then we will work on our